Hello everyone, and welcome to this our 14th weekly Ask an Astronomer stream, where I'm here with Aoife, and we're here to basically answer any questions you have about anything astronomical. We'll try and answer them all, but no guarantees, especially if you go for some niche questions. I'm Sam. I'm a PhD student at the University of Cambridge, and our regular viewers will notice that for the first time ever, Stefan is not here as one of us. We've given him a well-deserved week off, but I think he is loitering in the chat to make sure that things don't go wrong. So as I said, I'm joined by Aoife. So do you want to introduce yourself?
Yeah, so I'm Aoife. I'm also a PhD student at the University of Cambridge, and I'm really interested in looking at the relationship between the central supermassive black hole inside every galaxy and its influence on the galaxy that it lives in. And I look at really distant objects, and I use a technique called gravitational lensing, which you can see now up on your screen. This is an example of a gravitationally lensed galaxy in which we can see a very distant blue galaxy lensed into a ring we call an Einstein ring, and we can use this to study more distant objects that tend to be fainter, and we can study these in more detail, and just because they're magnified, which is really cool.
So how does the kind of magnification occur in these objects?
So it depends on your alignment of the system, but it's just the way that light, so every massive object bends what we call space-time, bends fabric space-time. So as the light from this background galaxy travels towards us, and if there is a massive galaxy or cluster in the way, this will bend the light so it magnifies around to us, and the amount of magnification depends on the orientation and how massive the lens is. So if you've got a more massive lens, you're going to have a bigger magnification.
Cool. So we've had a lot of questions coming in before we started, which is good. So we should probably get started with them. So should we start with a question about what nebulae are? Nebulae or nebulas? Aoife, do you want to go with that?
So there are two types of nebula. One we call star-forming nebula, which has a very kind of obvious name to it. So this is big clouds of gas and dust, and this is where stars form. And then we have other nebula called planetary nebula. Now, these are not where planets form. Instead, this is where you have a small star like our own or smaller, and it goes into its white dwarf phase, and then it expels all its outer layers of its atmosphere, and you get different pretty colours of its atmosphere left behind, and we call that, all these clouds in the atmospheres, we call that planetary nebula. So very confusing name, but
yeah, this is. I think I was on last week and I mentioned this, that in astronomy we have some really confusing names. I apologise for them. Yeah, planetary nebulae.
Or we just.
Yeah, nothing to do with planets.
We just can't be bothered to change the name. No.
Yeah. Okay, so we've got a kind of cosmology question here, asking about the relationship between the Big Bang and kind of a big bounce, and whether the Big Bang was just a kind of collapsed universe rebounding back. The answer to this question is no one knows, as in a lot of these kind of Big Bang-esque questions. But one of the ideas is the problem with the Big Bang theory, or one of the problems which people have thought of is, how does it start? You kind of need this beginning of why everything kind of kicked off. And one of the ideas is that, well, you might have universes which expand out for a while, but then the gravity is strong and that starts to pull things back together. In exactly the same way as if you throw a ball up on Earth, it comes back down to Earth. You might fire everything out of a Big Bang and it might all come back together in what's called a big crunch. And there's one kind of idea that maybe it wouldn't all just kind of crush together into an infinitely small point, but it would bounce back again. And you might get this kind of repeating cycle of big bounces, where the universe kind of comes out and back again over and over again. There's no real way of knowing whether our universe started like this or didn't, but we can think maybe about what our universe will do in the future. And historically, people have wondered whether our universe will carry on expanding forever. So if you were kind of strong enough and completely superhuman, you could throw a tennis ball upwards from Earth fast enough, then you could escape Earth's gravity forever. Is essentially what happens when we launch kind of rockets out to Mars and to the distant reaches of the solar system. We give them enough speed so they'll never come back. So the question whether our universe would carry on expanding forever or whether it would collapse back down again to Earth, to one point. And the consensus seems to be now that it will carry on expanding forever through something called dark energy. And I see we've got a question in on dark energy, which is perfect timing. So I'll save my explanation of dark energy for a bit later on. But yes, so we don't know whether our universe started from a big bounce, but the consensus seems to be that our universe will carry on expanding forever. It will never kind of collapse back down again. Good. Hopefully that explains that. So, completely changing scale. Question about whether it rains on Mars. Aoife, what do you think?
I don't think so, but it could have done it in the past. Because currently we don't think there is any water on Mars, therefore it can't rain like it does here on Earth. But there are a lot of theories and possible evidence that it could have there could have been liquid water on Mars in the past. So maybe it rained in the past on Mars, but I don't think it currently rains on Mars.
I think I'd agree with you there. So again, we seem to be jumping around a lot. I love these streams for this reason. So question on Hawking radiation, which we kind of briefly talked about last week, but it's asking how, if we have a black hole which is infinitely dense, then how can it kind of evaporate by Hawking radiation? So for those of you who weren't here last week, I'll briefly explain what Hawking radiation is, and then we'll cover the question. So when we have black holes, like let me get an image of a black hole up here. So when we have black holes, say like this, then inside what we call the event horizon, which is this kind of the ring you can see here between the black and the rest of the image, the gravity is so strong from the black hole that nothing can escape, not even light. So nothing can go faster than light in the universe, and the gravity there is so strong that light itself can't get out. But Hawking radiation provides a way for black holes to actually lose mass over time and evaporate, which seems impossible. If nothing can get out of them, the kind of so-called eternal prisons, how can they evaporate? Well, quantum mechanics, as it so often does, provides really wacky ways to do things that you don't think should be possible. And what quantum mechanics says is that you can create something essentially out of nothing. So if you have, say, in a region near the black hole, completely spontaneously you could create two particles, kind of an electron and a positron, which if they collided again would annihilate and just give out energy in the form of light. And they can be kind of created due to quantum uncertainties, and usually they just annihilate with each other. It's as if nothing happened. But occasionally you could get them where they're immediately separated by large distances, say by the gravity of the black hole, and one of them could fall into the black hole and the other one could escape to infinity. And so you just randomly create two particles, one would fall in and one would go out. But the thing about relativity, which is what this theory that Einstein came up with, which is what gives us black holes in the first place, is we have to think about what we would see sat here on Earth observing this black hole. And all that we would see is the fact that an electron, say, has arrived from the black hole to us. So some energy has essentially come out of the black hole. And the only way for that to happen must have been for the black hole to have lost some energy or to have lost some mass. And so the black hole must get smaller. So the question specifically asks, how does this get energy out of the black hole? And it's kind of weird because you're talking between different frames of reference. And in relativity, that's not entirely kind of straightforward to think about. So we should think about it from our position. We're sat here, we're observing the black hole, and energy comes out of it, and therefore the black hole has to lose mass. There's no way around it. So hopefully that answers your question. We're getting a couple of questions about the Fermi Paradox, about life on other planets, and whether there are any solutions to the Fermi Paradox. So do you want to kind of give a brief overview of the Fermi Paradox and then your opinion of it?
I think you might be slightly better positioned to answer this one.
Okay, I'll I'll explain the Fermi paradox, and then I'm still interested in your opinion though, because this is one in
Mhm.
which opinion is a good question. So Fermi
Mhm.
paradox, which was phrased by Enrico Fermi, about why we should essentially observe other life in the universe, and he went, there are so many stars and so many planets around those stars that there should be some life out there, and we should be able to communicate with it. And he came up with a long equation, which is basically the number of planets in the universe times the fraction of those planets which could support life times the fraction of those planets which life starts, and then the fraction of the times when you have life that it takes intelligent life to evolve, and then that intelligent life, whether it would get to civilizations which could be observable from a long way away, so civilizations that send out radio waves into space, and probes and that kind of stuff. And it's just a big equation, and you can put random numbers in and you get anything from no civilizations in a galaxy to hundreds of civilizations in a galaxy, depending on what parameters you put in. And it's kind of been, what's the limiting step? We haven't seen life out there. We don't know that it doesn't exist. We don't know that it does, but it's not as common as you might expect. And the question is kind of what the limiting step is. And I don't think there's not a concrete way of explaining this
Mm-mm.
yet. But I don't know if you have an opinion on what you think the likely limiting step is.
I think the likely limiting step could be communication. I think
Okay.
if we make the assumption that, say, every star has a planet going around it, and we're finding that this is like the most probable thing in our galaxy. So say our galaxy has 1 billion stars, there must be then 1 billion planets, and surely at least one or two of them must have life. But the problem is communicating with that life. Say we have Voyager, the space probe Voyager, that was Voyager 1 and Voyager 2. The Voyagers went up in the 70s, and only in the past few years have they just left the reaches of our solar system. So if we've only been able to send space probes that far, then say another civilization could also maybe be at the same evolution step as we are and still struggling to send communications out there to other planets. So I can't remember the distance to our nearest star, but say that has a planet, and I think it now does. That's going to take ages for those space probes to reach there to get communication in the first place. And then if a civilization has developed that the way of communicating with us through whatever it may be, then is that civilization looking at us and go, oh wow, they're really primitive, do we even want to make contact with them? So these are all like hypothetical situations. So I think there might be life out there, and I think it's just a matter of time, but we don't currently have the technology to do so. And as you go further into, say, our galaxy, these stars, they're so far away that potentially when they're looking back at Earth, when we look at other objects, we're looking back in time at the light that was emitted at X amount of time away. So are these alien civilizations that have all this tech to find us, are they looking back at us and potentially seeing us back in time, so potentially when we were primates still, and they'll be like, well, there's no way these people could communicate with them, these guys are not intelligent life. So there's a lot of open questions, I think, and it's quite exciting seeing kind of all the new theories, but I still think we're really a long way off.
Yeah, I think
maybe in our lifetimes, but
I think the time delay is an interesting point. I think certainly under lockdown, everyone's had the problem of the really laggy internet connection where you have to wait a few seconds for the answer, right? But here we're waiting years or thousands of years to communicate, tens of thousands. It's ridiculous lengths of time that I think that's a really good point. I'm more skeptical than you, I think. I think there might be life itself getting started. I think there's still a lot that we don't know about that, to say that there's definitely life out there. But I think the next the next 30, 40 years in the search for life is really going to tell us a lot about whether we can find life out there. Good.
I think it's probably more likely going to be microbial life versus humanoid things, because so far-fetched, but it's still hopefully promising.
Hopefully it will be very cool if we do find it. It would be so cool.
Fingers crossed.
Yeah. So back to black holes. I have a question about if black holes suck in everything as well as light, do they get bigger? Short answer, yes, they do.
Mhm.
Anything that falls into a black hole makes it bigger. Just the
Mhm.
amount of mass you get in there, really. So we have some really, really massive black holes that we can see, and they get that way. They don't form that big, they grow that big
Mhm.
by eating other things. And that actually ties in with another question I saw. We've got getting loads of questions in this week. It's really great. I'm trying to keep up with them all here. A question asking how the supermassive black hole of the Milky Way compares to other supermassive black holes out there, and specifically the one in Andromeda. Um, I'm not sure how big the one in Andromeda is off the top of my head. I'm trying to do a quick Google. But in general, the black hole in the center of our galaxy, the Milky Way, which is called Sagittarius A star, is quite small by the standards of black holes. So we tend to refer to, we tend to think that all, as astronomers, we're now fairly confident that all galaxies have a very big, we call them supermassive black holes. We like exaggerating in astronomy, so supermassive kind of gets the point across in the center of it. And the one in the Milky Way is about kind of a million times the mass of the sun, something like that. Um, which you might think is quite big. You know, the sun is like a million times bigger than the Earth, and this black hole is a million times more massive. You know, more actually kind of more mass than the sun, but that's comparatively small compared to some of the black holes that we see out there. So in your kind of work on quasars, you must come across these real monsters all the time.
Yeah. Yeah. So maybe we should quickly explain what a quasar is. So a quasar is what we call an active galactic nuclei. So this is where the black holes, supermassive black holes, actively accreting, so material is falling into the black hole, and then as the material falls into the black hole, it's heated because it's losing energy, it's losing momentum, so it has to fall into the black hole, and it's producing lots and lots of light that's really hot. And we observe this light from this black hole, and this light, it tends to be brighter than the light from the host galaxy. So when we're observing these quasars, we're just observing the light from that central region rather than the host galaxy. So yeah, I'm measuring black hole masses of say 10 to the 9, so 10 a billion solar masses, a billion times the mass of the sun, which is huge. And my objects the light from my objects is about 10 billion years old. So these are quite massive objects at earlier times in the universe. So these are really big objects.
Yes, so these are 1,000 times bigger than our own black hole, as it were. So yeah, our black hole is a bit puny by intergalactic
Yep.
intergalactic standards. So I think I'm trying to kind of jump into questions that follow on. I think someone asked about how we can look back in time and what you mean by looking back in time.
Mm-hmm. So when we actually, so say we take our sun for example, we see the light from our sun every day, and the light we are observing from our sun was actually emitted by the sun about 8 minutes ago. So we're actually seeing a delay in the light from the sun by about 8 minutes. So we're actually looking back in time at the sun, and then when we observe, say we're observing stars, galaxies, whatever, the light, because the distances are so big, it takes light, right? Light can only travel at the speed of light, it can't travel any faster. And when you're dealing with such incredible distances, it takes light time for it to reach us. So what we're doing is we're observing the light emitted by that object, however long it took to reach us, rather than the light it's currently emitting now, if that makes some sort of sense. So we're essentially we're doing a lot of time travel, and we're looking back in time at all our objects. So the more distant the object, the further you're looking back in time.
So your objects, which you're seeing 10 billion years ago, so the age of the universe itself is only 13 or 14 billion years old, and your objects being 10 billion years ago, that's really kind of early on in the evolution of the universe. Good. Okay, so where shall we go? I'm quickly scanning the chat. Actually, we've had one come
There's so
in.
many questions.
we've had one come in not on YouTube, which I think is an excellent question. So asking, can stellar black holes be held up by neutron degeneracy pressure but obscured from observation by the event horizon? This is a great. I love this question. So X Abyss, who sent this in, thank you. So I think what you're suggesting is, so in this image, for example, we can't see anything that happens within the event horizon because light can't escape. And so theoretically, you might expect that anything could be going on in there, and we'd have no idea about it. There could be people walking about on planets, etc., and it would all be fine. And so, to kind of backpedal a bit and give a bit of background for everyone, neutron stars are what we think of as the densest objects in the universe that aren't black holes. So when stars die, and big stars die, they leave behind a compact remnant, which is either a neutron star or a black hole, depending on exactly how massive it is. And neutron stars are held up by something called neutron degeneracy pressure. And this is a quantum mechanical effect and is really complicated, but I'm going to try and give a 30-second non-mathematical overview to this, which basically says that in quantum mechanics, some particles don't like being in the same place as other particles. And so there's only a finite number of places that particles can go, and therefore objects can only be so small. So if you take an amount of matter and try and squash it down, eventually the fact that you're trying to get these particles very close to each other means that they resist. It's almost like you can think of it very loosely as trying to pack a lot of people into a room. Eventually you can only get so many people in before you can't get any more in. They won't fit through the door. And this is kind of what neutron degeneracy pressure is. It's when you try and get neutrons, which are some of the things that exist inside the nuclei of atoms. So in atoms we have neutrons and protons in the center and electrons whizzing around the outside. And these neutrons, if we try and squash them together, they don't like it. Neutron degeneracy pressure, which is the thing that holds up neutron stars. Interestingly, the white dwarfs that Aoife mentioned much earlier when talking about planetary nebulae are held up by electron degeneracy pressure. So the same thing, but with electrons. So these neutron stars, when they get so big, it's roughly estimated to be about 2.3 times the mass of the sun, that pressure is no longer strong enough to overcome gravity. So gravity is trying to pull everything inwards, as it does on Earth. It pulls us down onto Earth. It's trying to pull everything in, and neutron pressure is trying to hold everything out. But when the gravity gets so strong, when there's enough mass, that neutron pressure can't hold it up anymore, and everything collapses down into a black hole. So hopefully that's the very quick background to what's kind of a third or fourth year university theoretical physics concept. Which unfortunately we don't have time for here, and would be quite difficult without a blackboard. So the idea that we could have a kind of a neutron star essentially inside the event horizon of a black hole, it's a nice idea, but it runs up against a problem in relativity. So this is a weird thing to think about, but one way to think about a black hole is to imagine your future. Now, say I can walk anywhere at 1 meter per second, right? Now this means that there are certain things that take me a certain amount of time before I'm able to do them. For example, my cupboard, which is behind me, is about 2 meters away from me. So walking at 1 meter per second, it will take me 2 seconds to get there and open it. I can't open it in 1 second because that would require me to walk faster than I'm able to do. Now, because light is the fastest thing in the universe, light sets this speed limit. So there are some things which take me a certain amount of time before I'm able to get to a certain position. And this defines all my possible futures. So all my possible futures lie in things that I can get to without travelling faster than the speed of light. So I'm probably currently a couple of hundred miles away from Aoife. She's up near London, I'm down in Devon, and so, travelling at the speed of light, it would take me not a very long time to knock on Aoife's door if I was able to travel really fast, but I couldn't do it instantaneously. But gravity affects my future. And what a black hole does is it means that my entire future, whatever I do, eventually ends up in the middle of the black hole. This is what relativity says. This is now ignoring quantum mechanics. So whatever I do, I have no choice. Once I've crossed the event horizon, that circle there, I have no choice but to eventually end up in the center of the black hole, right in the middle. I can do things to delay it. I can kind of try and turn around and try and run out of it. If I was in a rocket, fire my engines in reverse and try and get out of it. But all I can do is delay it. I can't stop it forever. My entire future, once I've crossed the event horizon, will lead me to being in the middle of the black hole at some point. So, although it's a kind of nice thought and it seems intuitive that anything could be happening within the black hole, the gravity is so strong that everything that enters the black hole will end up in the center. So the answer to the question is no, but it's a complicated answer. I hope that kind of made sense. It's a bit long-winded, unfortunately, but hopefully that works. Okay, so let's look for. You ask nice, hopefully quick question as a change up to that. Asking what would happen if you took a helmet off in space. If you're an astronaut on a spacewalk and you took your helmet off.
Oh dear. I wouldn't recommend doing that, to be honest.
No, I definitely wouldn't recommend it. There's no air in space, so there's no pressure. So basically you'd explode. Definitely don't recommend it. Kind of all the air that's
Nope.
currently inside you would immediately rush out into the vacuum of space, and you wouldn't survive very long. Okay. Nice question here about the difference between a quasar and a Seafoot galaxy.
Okay. So, technically, there's no difference between a quasar and a Seafoot galaxy. They are all types of AGN. The difference being is that we're looking at the AGN from a different angle. So, say you've got this is going to be really bad, but you've got your black hole in the center somewhere here, and it's got two jets coming off it, as we can see in the image as posted by Sam. When you're looking at a quasar, you tend to be looking down towards the jet, or at a slight angle to the jet. Whereas if you're looking at a Seafoot galaxy, you can see that we're looking at it from the side, so we can see these two massive jets coming off, and we tend to see these in radio. So you have two types of Seafoot galaxies, and this just depends on where it's the most brightest in the jet. So if it's in the edges, kind of at the top of the jets, or if it's close to the black hole. So yeah, they're both types of AGN, but it just depends on which angle you're looking at. The AGN is what you see.
And there's lots of other types, kind of broad line, narrow line, all these kind of things, which again were named because of the observations of them, and it was only much later that people realised they were all essentially the same thing. We were just looking at them from different angles. Cool. So, question here asking about gravitational waves. So, saying that gravitational waves pull and kind of push things as they go along, and asking whether they can rip you apart if you're very close to merging black holes.
I think you might have another problem if you're very close to merging black holes, to be honest.
Yeah, I wouldn't recommend getting close to merging black holes. I'm trying to think what I think the answer is to this one, but I'm not certain. I'd imagine that it wouldn't be very pleasant.
No.
I think you would have problems.
But
I'm not sure whether it would actually.
Apart.
I'm not sure. I don't have a kind of good intuition for how strong they are. A kind of at their peak power, so the amount of energy that's carried away um, in these gravitational waves. At its peak power can be kind of more energy going out per second than kind of the sun generates in its entire lifetime. They are ridiculously energetic sources. But whether they have enough energy to rip you apart, I'll have a think about it, and I'll try and whoever's on next week, if you tune in, I'll tell them to answer this one when I've had a look at some of the numbers. Hopefully, this proves that this isn't scripted. We are literally just going on whatever gets asked. Okay, this one from I think the same person asking about if the black hole in the center of the Milky Way becomes active, whether that would be dangerous for us or not. Any thoughts on that one? What do you reckon?
I want to say that we're too far out. So where we are in the Milky Way galaxy was actually we're in just at the edge of one of the spiral arms. So I don't think we'd be immediately too affected by it. But I think other stars closer to the black hole might have a bit of a problem. But I think we'd be fine.
I'm inclined to agree with you on that one. I think so as Aoife mentioned, these black holes, as they eat material, they fire off these jets. So maybe potentially if this jet happened to be pointed directly towards the Earth, but I don't think that's like they usually kind of come out of the edges of the galaxy. So our galaxy is kind of disc shaped and flat, and the jets would usually kind of come out the top and the bottom, and not fire through the galaxy towards us. So no, nothing to worry about. And also if it did become active again, this would only happen over kind of the course of millions, if not billions, of years. So there's no imminent danger, definitely. Good. Let's have a look. So a question asking about the galaxies, about dark matter in galaxies, and asking about whether they're therefore kind of dark in colour. So kind of the general, we can kind of chat about the general role of dark matter in galaxies, and there's a picture for this one. There we go.
Yeah. Okay, so we think dark matter is called dark matter because it is matter and it is dark. We can't see it. A very creative name for our astronomers, and it was first discovered. If you look at the rotation curve of galaxies, so if you look at, say, a spiral galaxy rotating, what we expect to see is that the rotation of the galaxy drops off, so it decreases a function of 1 over r squared, and this is just Newton's law of gravity. But so we would expect it to do this dashed line, as we can see on the screen here. That's what we'd expect to see it just drop off. However, when I think it was Vera Rubin that observed these, I think there was multiple people that observed these. When they observed the rotation of these galaxies, what they actually discovered that as you went towards the outer edges of the galaxy, their rotation didn't drop off, and this actually increased a little bit or stayed constant to several parsecs beyond this. So the typical size of a galaxy is about 8 parsecs in diameter, so double that, about 14 parsecs. 8 parsecs in radius, so double that, you get 14 parsecs across in diameter. And then beyond this, by several parsecs, this rotation curve didn't drop, which suggests that there must be more mass there that we can't see that is, keeping this rotation curve constant or increasing. So, and we think that around every galaxy there's all this matter that these galaxies sit in, and this causes the rotation curves to stay constant or increasing. So we can't see it, unfortunately, and I know there's lots of simulations, I think, that colour it, but that's like false colour, just to kind of get an idea of what's going on with all the dark matter. But we can't see dark matter, which is why it's called dark matter. We just know it's matter, and it's dark, and it's there.
So in terms of
which is really pain.
It is a massive
it's such a pain.
So in terms of kind of the galaxy in this image, the colour comes from the stars and the normal matter that we can see. So the dark matter doesn't affect kind of the light that we see in terms of what colour it is. There's a question from a lot earlier which I noticed and then promptly forgot about, but is a really cool question. I can't find it now, but it was asking about oh yeah, is whether there's a cloud in space that tastes like raspberries, which goes back, I think, to I don't know if you remember this. I've had to Google to find the place I saw this about 10 years ago. Scientists or astronomers discovered ethyl formate, which is a kind of relatively simple uh, molecule which they found in a gas cloud near the center of our galaxy, which is the chemical which gives raspberries one of the chemicals which gives raspberries their distinctive taste. Um, and they found it out in space, and it led to many great headlines about space tasting like raspberries. Um, so in a sense,
That'd be
yes,
quite cool.
there is a cloud out there that tastes like raspberries, but I mean, there's lots of other things that are required to make a raspberry a raspberry. I think.
Mhm.
Cool. Um, so, question about whether we can make black holes out of dark matter. This is, I think, a relatively quick one. The answer is yes, you can.
Mhm.
Any matter that falls into a black hole would add to the mass of the black hole, and theoretically, if you could get enough mass, enough dark matter into a small enough volume, um, then yes, it would form a black hole. But there's kind of one potential issue with that, which is so when normal matter collapses together and forms things like stars, you can imagine all the matter falling in, and the only thing that stops it kind of flying through itself and off the other side is the fact that it interacts in ways other than gravity, or the main way that it stops it doing this. So in kind of big clouds of gas, you might have things falling together, and then lots of collisions between the molecules in those clouds lead to dissipation of the speed or the kinetic energy of the material into heat, and that kind of stops the clouds flying through each other because they've suddenly lost a lot of energy. And so what they do is they might collide once and then come back together and eventually kind of coalesce into one more massive cloud. Dark matter doesn't do that, so it doesn't interact with itself in the same way, because it only interacts via gravity, and therefore dark matter, if it did, you kind of had it collapsing, would fly through itself and off out the other side, and so it's very difficult to imagine a way in which you could make a black hole completely out of dark matter, because it would be very difficult to kind of get it all in a small enough space to begin with. But theoretically, yes, you could, and certainly any dark matter that happens to fall into a pre-existing black hole will stay there. It's it's not going to go anywhere. Good. Um, I think we're getting through the questions
Mhm.
relatively well. I'm worried I've kind of missed some earlier on. There was one from towards the beginning, kind of talking about the amount of energy that the sun radiates. Um, about that one, and kind of how powerful it is. So
So the amount of oh,
go
go on.
ahead. No, go ahead.
I was gonna say the luminosity, which is like the power output per second, is about 10 to the 26 watts. So that's 10 followed by 26 zeros watts. So I can't put that into billion. It's billion. Can't do that.
Billion,
Billion.
nearly a billion.
Billion.
It's really big.
So billion, almost watts.
Yeah, and for kind of context, kind of the light bulb that's up there, which you can't see, but it's up there, is kind of 50, 50 watts, maybe something like that. So these are kind of whack 25 zeros onto the end of the amount of power coming out of that light bulb, and you kind of have the amount of power coming out of the sun. It's it's colossally big. numbers. I mean, one way of thinking about it is the sun is what keeps the Earth warm, essentially, and the sun is what 150. Gotta get this right now. How far away it is? I always get this number wrong. Like 150. I'm gonna have to Google this now.
It's 10 to the 11.
Yeah.
It's 10 to the
150 million kilometers, something like that. Yeah, that's right. There you go. 150 million kilometers away. There we go. Or about 100 million miles for those of us who still work in imperial units. There's a kind of colossal distance away, crazy, and it heats the Earth still, and it keeps the Earth at its temperature, average temperature of about 15 degrees. A small amount of the energy comes from the Earth itself, from kind of the inside of the Earth, but most of it comes from the sun, and it's doing that from 100 million miles or 150 million kilometers away, which is a kind of a pretty staggering distance. A new question which I think has come in specifically for you, Aoife, about
exciting.
whether in your research you've come across any particular quasars which are of special interest. Have you got any favourite quasars?
I think it has to be the first quasar I studied. It's probably my favourite quasar I studied because it's where I did most of my learning on sort of properties of quasars and then gravitational lensing as well. So this quasar, which I can't talk too much about because it is unpublished, but it's essentially what we call a Einstein cross. So if we go back to the image of gravitational lensing.
Let me get that. There we go.
So here we see a lensed galaxy, but in the case of a lensed quasar, because the light is coming from such a small region, so it's coming from that small region around the black hole, what we tend to see is, rather than a ring, we tend to see dots. So we tend to see two or more images of the same object. So with this quasar, what we see is 4 images, which is what we call an Einstein cross, which is slightly more rarer than we usually tend to see sort of 2-image quasars. And the reason why there's a difference between the two, it just depends on the alignment. So if you have your background quasar directly behind the galaxy or cluster that's doing the lensing, so in this case we have a galaxy that's doing the lensing, then you'll see either an Einstein ring if it's just a galaxy, or if it's a quasar, then you see 4 images. So yeah, I have a quasar that has 4 images, which is really exciting, and this could also mean that if we looked at different wavelengths of light in different images, we may be able to see the host galaxy of the quasar as an Einstein ring, which is what you tend to not be able to do if you don't use gravitational lensing, which is why it's a really useful skill, because you're able to separate the light from the quasar and the light from the galaxy and study these 2 things separately to really get an understanding of what is going on between the black hole and the host galaxy, because there's a lot of theories, but it's definitely not well constrained on what's happening, and these 2 things seem to evolve together, even though the black hole may only influence the central region. So it's really, really exciting. And yeah, my favourite quasar is the first one. The first one I studied because I learned a lot about quasars and had to do gravitational lensing and study gravitational lensing, and it's a 4-image quasar, so that's really cool.
I think the first piece of research
Sorry for the ramble.
No, I think the first piece of research you ever do always kind of sticks with you. And yeah. So we've had a question about dark matter and dark energy and whether they're related, and specifically whether they are just hypothetical ideas. So as Aoife mentioned earlier with the dark matter, we expect to see dark matter originally from observations like this of galaxy rotation curves, but also there's evidence that we need more matter when people study how galaxies form. So the way galaxies form is a really complicated process to model mathematically, because what basically happens is you have small fluctuations very early in the universe, and wherever you have a region that's slightly more dense than a neighbouring region, gravity causes matter to fall onto the more dense region, because the gravity from that region is stronger, and so gradually it gets bigger and bigger and more massive, like so. And so kind of galaxies form in this way just from collapses of matter under gravity. And that process is essentially still going on. It's been going on for the past 13, 14 billion years since the universe began. And this study, it's not easy to kind of explain this intuitively, but if you do the modeling, it turns out that you need more matter than we can observe. And so this is, again, supports this idea of dark matter. There are some people who think that we don't need dark matter, that we just need to change the laws of gravity. So since general relativity 100 years ago, that's been our fundamental kind of theory of gravity ever since, developed by Einstein in about 1915. But these tend to be less common, and most people think that dark matter exists, and that we need it. Dark energy is kind of completely different. So I'd say they're not related specifically. And dark energy is a really weird concept. It's basically the idea that space tries to expand on its own in a weird way. It's like, so normal matter pulls objects towards it. This kind of dark energy pushes everything apart, and it does so at an ever increasing rate. So if dark energy was all there was in the universe, things would just get further and further apart. And no one really has a good idea why, as far as I'm aware. People have theories. Some people think it's just an artifact of space, the fact that space exists and it behaves like this, and it just naturally expands. But there's no real consensus about it. But we have good evidence that it should exist. So in Einstein's theory of relativity, there's a very easy way to add this dark energy into the equations. And in fact, Einstein did it originally way back in 1915, and he then described it as his biggest blunder. But now this same way that, Einstein he's so great that even when he makes a mistake, it turns out that it might actually be true much later on, in ways that he couldn't really have conceived. But we can add this dark energy to our models of the universe, and just let them run, and it turns out that these models with dark energy, they just work much better. They fit what we observe. And we now think that of all the energy in the universe, about 70% of it is this dark energy, 25% of it is dark matter, and only about 5% is matter that we can see and touch and interact with. So you could say that all of physics up to now has been working on explaining only 5% of the stuff that actually exists in our universe. But in a sense, they are hypothetical, because the evidence for them observationally is sort of indirect. If you know what I mean, like, no one's actually observed it directly and said, look, here I have some dark matter, or here there's a piece of dark energy. But their effects are observed and they fit what we think should happen quite well. So astronomers in general are fairly convinced that they both exist. But there's a good kind of follow-up to that, asking about, I'll bring it in here onto the rest of the screen. I'm trying to juggle all the chat windows. I didn't set it up properly beforehand. About recent observations and maybe leading to machos being reconsidered as dark matter candidates. So yeah, since dark matter was first kind of suggested, people have been kind of trying to work out what it could be, and there were two kind of opposing theories called Wimps and Machos. This is really, I think, the start of when astronomers fell in love with acronyms that are funny words. So Wimps, I think, came first and was a normal acronym. They stand for Weakly Interacting Massive Particles. And these are basically what Aoife talked about earlier. They're subatomic particles that only interact via gravity, essentially. They might interact in other ways, but just very, very rarely. But essentially only via gravity. So they were Wimps. And then the alternative were coined Machos, which are massive compact halo objects. So the MA came from massive compact halo objects. I think it was fit to try and make it fit macho. And the idea here is that there's lots of bits of normal matter. So for example, there might be lots of black holes which we can't see, floating about around galaxies and providing this extra matter that you need to fit these observations that are on the screen. And this idea has fallen out of favour because, well, I mean, this ties in with the lensing stuff that you've been talking about. Even though we can't see these black holes with kind of direct light, when they pass in front of other stars, they should produce this lensing effect. So on a very small scale, they should kind of create these rings on individual stars when there's a star behind the black hole. And people have searched for this and they haven't found any. And so this means that if these kind of compact halo objects do exist, they can't be very big at all, and only kind of a few times the mass of the sun. But some people are still, I'm not aware of any specific new observation that's come in about. I don't know if you've heard of any, but there has been some discussion about that they could be kind of black holes which are only kind of a few times bigger than the sun, just loads of them, like billions and billions and trillions probably of them, and maybe that could, if not be all dark matter, then some of the dark matter. And we haven't been able to rule that out, but there's no real evidence in favour of those either. Yeah, so hopefully that covers those questions. Interesting question asking about the solid matter of the Jovian moons, where that comes from, and whether kind of out where Jupiter is, why there's any kind of rocky material, and why isn't it all just gas on that one?
Well, I suppose we kind of first need to ask where all these elements above hydrogen and helium, which tend to form in the sun, where do they come from? And I quite like this because it's really sweet, but also it shows that the universe likes to recycle itself. So when massive stars die, really massive stars, they go supernova. So what they do is they basically throw away all their outer layers as such incredible energies that they force particles and elements together to form heavier elements. So in the centers of massive stars, we're talking way bigger than our sun, you can form all the elements up to iron, and then beyond iron you can't form any more because more energy is needed to push them together than would be necessary. So when you fuse elements, you push them together and then release energy, and that's how the sun keeps going, the stars keep going. But anything above iron is just not it's not viable really. But in supernovas, the energies are so great that they force these heavier elements together. And then also in supernovas, this could, as they sort of explode, these could also trigger star formation on nearby nebula, so star-forming nebula like we talked about earlier. This could trigger star formation, and star formation can happen that way. And because the Jovian planets are sort of so far away from the star, our sun, these cooler elements can form. I don't think you have anything to add to that. And when stars form, it's not necessarily all the stuff that comes into the star. Bits are left around it. It's not all like everything goes into the star making. You have like the central bit, things fall onto the central bit, but you also have this like ring around it of material which will form the planets. Mm. Are we muted?
I'm muted. I apologise. I muted myself so that I could have a drink and then forgot to unmute myself. Apologies. Let me backtrack about a minute on that one. There we go. I said there might be technical issues. So Yes. So I was saying that hopefully that's fixed now. Okay, there, it's back now.
That's good. That's good.
So I said that maybe the original question is phrased slightly the wrong way round. So as Aoife said, when the sun forms and you have this disk of material around it, this contains like lots of gas, like hydrogen and helium, and then lots of the kind of the heavier elements that form rock. Um, Someone else has said there's no sound now, and now I'm worried. I think the sound is back. Can someone confirm this? Am I back? Can people hear me?
Like people can hear us. That's good. That's
okay,
good.
Okay,
we're gonna go
that's
with.
fine. That's fine. Okay, I'm gonna like make a third attempt at answering this question, and then I'm just gonna give up.
Translate for you, Sam.
I've lost my train of thought now. Yes, so disk of material around the sun, which contains all the elements from hydrogen and helium and the light gas, lots of that, and then small amounts of the things that form like the Earth, like carbon and magnesium and silicon, things that go into rock. Now, the bits that are close to the sun, when the sun kind of turns itself on and starts its kind of nuclear burning process, then that will heat up the gas that's surrounding it, and a lot of this hydrogen and helium will be kind of blown away by the sun. And so these really light elements can't exist close to the sun. And there's a thing called snow lines, which I love. I love this expression, snow lines or ice lines, when you're talking about forming planets or forming things around the sun. So if you imagine say that the sun was here, and as we go outwards, the temperature gets colder. So for each individual element, you might have, say, water. H, or it doesn't have to be elements, molecules as well. Water, it might be a gas very close, and then at some point it can become a liquid or become solid. Really, the liquid phases will be very small, so it goes from gas to being solid. And when it's a gas, it can't form into planets, and when it's a solid, it can. And different elements have different positions where they'd make that transition. So very close to the sun, where say we are Mercury, Venus, Earth, Mars, the so-called terrestrial planets, all this gas would have been kind of blown out by the sun, and it doesn't exist in there, and so there is no gas around. Out where Jupiter is, so the question asked originally, surely there shouldn't be any rock out there. There is rock, there's just so much more hydrogen and helium. So the core of Jupiter, kind of what's in the middle, we don't really know. There's theories that it might be iron in there, which has then got a big envelope of hydrogen and helium. Because when the planet gets big enough, its own gravity pulls in all this hydrogen and helium to make Jupiter, pulls in this envelope around it. But in terms of the moons, they never had gravity big enough to pull in this gas. So the Jovian moons would have formed in much the same way as Earth did, and Mercury, Venus, Mars formed. They just happened to form in a region close to a place where Jupiter formed, and Jupiter got all the gas, so that the Jovian moons ended up just being rocky. But we can kind of see this kind of snowline thing in the fact that out beyond Neptune, where all the comets are, there's lots of icy material. So lots of water ice and maybe other forms of ice as well, kind of other things in just solid form. And so because it's much colder out there, they could have formed, which is kind of, we can kind of see this in practice. I think we've got time for one more question before we finish. And actually, there's a couple of related ones from the same person here asking. Firstly, how do galaxies die? And similarly, how do galaxies stop forming stars? I think you mentioned about feedback here, but
okay. So the relationship I'm interested in is understanding the relationship between the black hole in center and the galaxy it's in. So what happens in star formation is you need this kind of cool molecular gas to form stars. But when you have an active galactic nuclei, what we think it's doing is it's also producing these winds, which heats up the gas, so it's too hot to form stars, therefore stopping star formation, or we call quenching star formation. But say you had, which happens quite a lot, and this is why we how we think a lot of the black holes in the early universe formed, because they're so big, and if they were to grow at their normal rate, they shouldn't exist, but they do exist. So we need some kind of way of explaining these. If you say had merging galaxies, then these two galaxies would come together, and there'd be so much dust and gas going on that you'd actually trigger star formation again, so start producing stars again. And how you've got a galaxy that has star formation going on is you tend to have bluer stars still present in it, so the galaxies look blue because the young stars are blue. But young stars, these blue stars, these white stars, they have very short lifetimes. They use up all their energy and all their resources very quickly and then die. Whereas your smaller stars, which are sort of your redder stars, they don't need as much fuel, and they sort of have these really long lifetimes. So when you look at galaxies, if you tend to see a more bluer galaxy, like we have on screen, there is a bluer galaxy. We can see this is a star-forming galaxy. Whereas if you see a sort of redder galaxy, this means that older stars in this galaxy. There's no sort of blue in there, which means this is an older galaxy with older stellar populations. And we have kind of two kind of types of galaxies. You can define them as. We have, okay, here's the really confusing bit. We have the early type galaxies and the late type galaxies. So the late type galaxies are the star-forming galaxies, and the early type galaxies are the non-star forming galaxies, and we call these elliptical galaxies, and these tend to form when two galaxies merge, two spiral galaxies merge. They trigger some star formation for a bit and then they stop, but the motions of the stars are not these lovely spirals anymore. They're a bit sort of messy.
Yeah,
but they tend to be more massive.
Yeah, yet another astronomers can't name things in sensible ways. It's another historical thing. But yeah, the kind of whole like galaxies dying and this kind of star formation stopping is a really open question, and the role of feedback and different things is, I mean, there's lots of people who are still working on this, some of them in our department, who are really trying to kind of understand these links. Cool. I don't think we've quite got to every question. I'm sorry if I've missed one of yours, but we have now been on for about an hour. So I think we'll stop here. Someone will be here again next week. I'm not sure who it will be, but please do tune in again. If you want to ask your questions, kind of any that we didn't get to in advance, then if you go to the kind of the Institute of Astronomy website, one of the links that's been going around up there is where you can actually ask your questions in advance, and then I can't point in the right direction because it's the at the top of the screen. One of the links. If I keep talking long enough, it'll come round and I can say this link.
There we go. There's a Twitter thing.
But yeah, if you follow us on Twitter and stuff like that, if you get your questions in advance, then whoever's here will try and get to them next week. But yeah, please do tune in again. But yeah, bye.
Thank you. Bye.